So we want to prove that the derivative of tangent of 3x is equal to secant squared of 3x times 3. By writing tangent in terms of sine and cosine, and then taking the derivative using the quotient rule. Now, it's really important here for these problems to read the specific directions, because you could also be asked to do one like this by using like the power and the chain rule instead. So there's multiple ways to do these, like the second one after that. So first step is to rewrite this, or to write it as the derivative of sine of 3x over cosine of 3x. We do have to know that tangent is sine over cosine, and cotangent is cosine over sine. And this feels really low. Is this just the... There we go, much better. Okay. So I feel really hunched over here. And let me see if I can find a pen that is. There we go. Cool. So then we're going to use the quotient rule. So it's going to be the bottom times the derivative of the top, and the derivative of sine of 3x is going to be cosine of 3x times the derivative of 3x, which is 3 because of the chain rule, minus the top times the derivative of the bottom, and the derivative cosine of some stuff is negative sine of that stuff times the derivative of that stuff, all divided by the denominator squared. I wouldn't normally write this if I was doing this problem on the exam, but I'm just going to point out, if we think of this in a normal like quotient rule kind of way, where the top function is f and the bottom function is g, then we exactly have f prime times g minus f times g prime, all divided by g squared, as we usually do. And you might notice I write my first part slightly out of order. I like to write g times f prime instead of f prime times g. That's totally fine. It's just the way I say it in my head. And then after this, we still have to do some simplifying, which is kind of the challenging part here. So I'm going to multiply this out. I'll take an extra step here. So I'm going to have a 3 times cosine of 3x times cosine of 3x is cosine squared of 3x. Minus times the minus is plus. Factor out the 3. It's sine of 3x times sine of 3x is sine squared of 3x. All divided by cosine squared of 3x. And then from the top, we should factor out a 3. And you're left with cosine squared of 3x plus sine squared of 3x divided by cosine squared of 3x. And now for this sort of problem, if it's either tangent or cotangent, you have to then use a trig identity. The trig identity is that sine squared of something plus cosine squared of the same something is always equal to what? 1. So I do like to be kind of explicit here. So like, oh yeah, that's equal to 1. So we're going to get 3 times 1 over cosine squared of 3x, but then dividing by cosine is the same as multiplying by secant. So it becomes 3 times secant squared of 3x. That's what we wanted. Kind of the way here. Questions about any of that? No, I went down the wrong way. Not terrible. Let's do the other one. Let's do part 3D just to see how the other one is different. Oh, excuse me. So that was 3. So for 3D, I will say for this one, for tangent and cotangent, you could do it. It's kind of weird. It's kind of weird to do it not using the quotient rule for tangent or cotangent. Excuse me. For secant or cosecant, you kind of have options. So if I want to find the derivative of cosecant of 3x, this is 3D. Specifically here, it says by writing cosecant in terms of sine, and then taking the derivative using the chain rule, not the quotient rule. So I'm going to rewrite this as the derivative of 1 over sine of 3x. But if I write it that way, I would have to use the quotient rule. So I'm going to rewrite it again, or I probably should have skipped that step and say, what's going to be the derivative of sine of 3x all raised to what power? -1. That's how we have to rewrite it if we're not going to use the quotient rule. Now we can use the power rule, the chain rule version of the power rule, right? You've got some stuff to the -1 power and the derivative of some stuff to the -1 power. Well, that's going to be -1 times our stuff to what should our new power end up being? Right, -1 minus 1. And then we have to multiply by the derivative of the inside stuff. The derivative sine of some new stuff is cosine of that new stuff times the derivative of that new stuff. And we can't stop here because we have to make our answer look like what they said it needed to look like, right? They say the answer should look like -3 times cosecant of 3x times cotangent of 3x. Now, I will say, if after you took the derivative, you just said it was equal to -3 cosecant of 3x times cotangent of 3x, you can probably get away with that. You probably be like, well, yeah, that is the thing it's supposed to be. I'm just going to write that. I'll show you the steps though. So, but I will point out, if you have a problem like this, and I would be willing to bet you're gonna have a problem like this because he's asked it a few times, right? It's not the only time he's asked a question like, show this thing is this thing by taking the derivative this way. You could probably just say that's equal to -3 cosecant of 3x times cotangent of 3x. Someone grading your work might buy that, but they're like, yeah, that's true. But here are the steps I personally would expect to see as someone who's written this question. I'm going to rewrite this as -3, and then sine 3x to the -2. I'm going to put that in the denominator as sine of 3x squared, or I should say sine squared of 3x, and then cosine of 3x on top. And now I'm just going to think about what I'm trying to get to. I'm trying to get to a cosecant. Well, a cosecant is a 1 over a sine. So let's just write that. I've got a -3 times a 1 over sine of 3x. And a cotangent of 3x is a cosine over sine. So I'm going to write that. And that is the same as what I had. Right? Cosine of 3x over sine squared of 3x is, I'll have a 1 times cosine on top and a sine times sine on the bottom, which is the same thing. So if you're not exactly sure how to get from this step to this last step here, just think about what you need the things to be, right? If you need a cosecant, that's a 1 over sine, write it. If you need a cotangent, that's a cosine over sine, write it. And then, oh yeah, that's exactly what we want it to be. So then I would be like, yeah, that's equal to that. Someone could ask you to do it this way, or they could ask you to do this problem using the quotient rule, right? Either way is a valid way of asking it. So if instead they said, use the quotient rule for this, let me just point out how it ends up being the same. So the derivative of cosecant of 3x is the derivative of 1 over sine of 3x. And now let's use the quotient rule. So it's going to be the bottom sine of 3x times the derivative of the top, which is 0. Welcome, Rocco. Problem 3 from my practice exam. Minus the, what? I forgot what it's doing. Bottom derivative of the top minus top times the derivative of the bottom is cosine of 3x times 3, all divided by the denominator squared. And look, we're exactly in the same spot we were here. Well, almost exactly. It's not okay. Like more like here, I guess. We've exactly gotten to -3 times cosine of 3x divided by sine squared of 3x. So either way of doing this type of problem, whether it's for secant or cosecant, and you're using either the quotient rule or the chain rule, should get you to the same spot. But I do strongly recommend for this, if you see this kind of problem, and again, I'm willing to bet it would be on there, make sure you read the instructions carefully so that you're doing the thing you're actually being asked to do. If they say, if they say, write it, make sure you use the right rule, right? If they say use the quotient rule, use the quotient rule. If they say use the chain rule and or the power rule, do that. So just read carefully. Questions about this one? Okay. Time for a 3-minute quiz. It will not be collected. We knew it was coming, maybe you didn't know, but you should have known. I threatened. Wow, okay, sorry. All right. Do it to it. Oh, for those of you on Zoom, here you go. You can do it too. Find those derivatives. So 3 minutes? Yeah, 3 minutes. Good. You could have gone right. That's fine. I'll remind you, every co-function has a negative derivative. Forty minutes. Try to be patient. Okay. Almost. Close enough. All right. So there's two I know you know. I know you all know sine and cosine. Oh, yeah, okay. The derivative, oh, stop. The derivative of sine is cosine of x. The derivative of cosine of x is negative sine of x. The other four, there are various ways you can remember them. I think I showed you all this before, but I'm going to show you it again because I think it's an easy way to remember things. I've had students show me that they like to do this. They like to write tangent goes to secant, and then an arrow coming from secant to tangent. So the derivative of tangent is secant times secant. The derivative of secant is secant times tangent. And you can do a similar thing for cotangent and cosecant. You can write cotangent of x, negative cosecant of x, cosecant of x. The derivative of tangent, the derivative of cotangent is negative cosecant times cosecant, which is negative cosecant squared. The derivative of cosecant is negative cosecant times cotangent. That's one way one thing you could use to memorize them. You do not have to use that, but it might be convenient. It's easy to write down. Yeah. So trig derivatives, you definitely need to know them. They're going to be on your test tomorrow. Make sure you know them. Cool. Questions about any of that? Other questions about either practice exam? Yeah.
Just related rates.
Cool. Sure. So let's go ahead and look at the related rates questions on both of the exams, and then we can do even more because I've got plenty of related rates questions over here. Let's make sure I've got things in order here. Yes. Yeah.
We like, I remember only one word.
Mm-hmm.
We know like, not every single one, but like the latter one, like every single shape one.
Yeah, I mean, yes, I would say the shapes are important. So let's like, yeah. So let me just we'll just do some we'll forget about the ones on this game. Let's just run through a few examples and talk about what you could be asked. So yeah, we'll do a bunch of examples here. So let's look at some related rates questions. Not that that's all we have to do, but we can certainly do a few of them. So let's look at some not too terrible examples. Like, for example, the side length of a cube is increasing at 3 inches per second. How fast is the volume of the cube increasing? I don't really think you need to draw a picture here, but it doesn't hurt to draw a picture. There's a cube. It is good to label the things that are changing, and we know that the side length is changing. So I'm going to label each side as either S or X are typical names. You can pick whatever names you like. So my side length X is increasing. So when I start writing down the things that are changing in step 1, I know that X is changing. I probably wouldn't usually actually write those words. I would just write that dx dt, the rate of change of X, is equal to 3 inches per second. So typically when I'm writing down the things that are changing, I'm always looking for the thing they told me and the thing they're asking me about. They told me how fast the side length is increasing. They're asking me how fast the what is increasing or changing. The volume. So I'm looking for what dV dt is. All right. After you have written the things that are changing, your job typically is to find an equation relating the things that are changing, the non-time variables. So we want to find an equation relating the side length and the volume. And it's usually just the geometrical equation of the volume of the thing or the surface area of the thing or the whatever of the thing. It's usually pretty straightforward from the picture you've got. Like, oh yeah, I have a cube. I want to find the volume. The volume is going to equal X times X times X, or X cubed. Step 3 is to differentiate both sides of this equation. It's kind of like implicit differentiation, where we're assuming everything is a function of another variable. In this case, it's time. So the derivative of v is dv dt. The derivative of some stuff cubed is 3 times your stuff squared. And if you left it like that, you have a problem, because both of my rates aren't showing up. This is a related rates problem. Both of the rates should be related to each other and show up in your derivative. And they should, because we didn't just take the derivative of x cubed, we took the derivative of a function of t cubed, or some stuff cubed. And the derivative of some stuff cubed is 3 times your stuff squared times the derivative of the stuff. Yes, if it's helpful, and it might be helpful, you might prefer to write this original equation as volume as a function of time equals side length as a function of time cubed. And then when you differentiate both sides, the derivative of v of t is v prime of t. The derivative of x of t cubed is 3 times x of t squared times x prime of t. There's absolutely nothing wrong with writing it this way. It is the same information conveyed as this, just written with different notation. It's more typical to write it this way. But if you write it this way, no one should have a problem with that at all. All right, we've done the important thing. In fact, I should point out, this is often the case, right? You don't, if you're trying to like find the equation of the tangent line using implicit differentiation or related rates using differentiation, you're always taking the derivative of everything first and then plugging in the values to solve for the thing you're trying to solve for, whether it's the slope of the tangent line, whether it's the rate of change of the thing you're asked about. So now we're going to plug in and we're going to get, let's see, so I'm plugging in 3 inches per second for X. Sorry, no, oh, as typical, I forgot to include an important piece of information here. So if we just plug in now, I don't know what X is. So typically they have to tell you the when or the what, right? So I should have said, how fast is the line when they keep increasing when the side length is 10 inches. So then we plug in and we get the dv dt, which is what we're trying to find. It's going to be 3 times, I'm not going to actually, 3 times 10 squared times dx dt, which is 3, like that. I will point out that 10 is 10 inches, quantity squared. That 3 is 3 inches per second. So you get inches squared times inches per second, which is inches cubed per second, which is the right units for how a volume is changing, which is good to know. So we end up getting 3 times 3 is 9 times 100 is 900 cubic inches per second. I do think when you answer a related rates question, at the very end, you should include the right units. You don't need to include the units like step by step, unless he says you do, but I don't think you will. But definitely at the end, you should write the correct units. And I will point out, if things are being measured in inches per second, and I'm being asked how a volume is changing, I know my answer is going to be inches cubed per second. If they said instead, how fast is the surface area changing, then our answer should be in inches. Sorry, I can't hear anything. What'd you say? Inches, how to the, is it inches per second or inches squared per second? If it's surface area. Yeah, it's inches squared, right? Because an area is inches by inches, inches squared. So basically, if it's an area, it's the thing squared. If it's a volume, it's the thing cubed. If it's just the length, it's the unit per whatever unit of time is. Seconds, minutes, hours, years, whatever. And that's always kind of how it works. So you know, oh, if a volume is changing, it should be your unit of length to the third power divided by your unit of time. That's what we're measuring. What if we did ask how the surface area was changing? Right? That's a good follow-up question. How is the surface area changing at the same moment? So now I have to go back and look at our box here. And we're like, well, okay, well, dx dt is still doing the same thing. Dx dt is still changing, or is still 3 inches per second. X is increasing at 3 inches per second. And now we're asking how surface area is changing. So typically we're going to say that S is the surface area. Or A. I guess you can use, I don't know, you can use whatever you want. I like to use S, some people like to use A. And so we're looking for ds dt. I will point out it's usually a capital S. I know that shouldn't matter, but it often is. Just like area is typically a capital A, not a lowercase a. So then we need the equation relating those non-times variables. Well, for a cube, each face is just x squared. And there's how many faces? We can see 3 of them. There's 6 total, right? There's these ones a bit back here too. Or when you say cube, you should really just think of a die, right? You're rolling a die or dice, right? A dice has 6 sides. A die has 6 sides. So our surface area here is equal to x squared 6 times. So 6 times x squared. And then if we differentiate both sides, we're going to get ds dt to 12x times dx dt. All right, the rest is plugging in. So now we're going to plug in, we're going to get that ds dt is equal to, I'm going to write the units this time just so you all can see it. 12 times x was 10 inches, right? The same moment as the previous problem. So we're asking how is the surface area changing when the length of a side is 10 inches. So x is 10 inches and dx dt is still 3 inches per second. I'm multiplying it all together. 3 times 12 is 36. 36 times 10 is 360. And inches times inches, so inches squared per second. As it should be if we're talking about how an area is changing. It should be inches squared per second, or feet squared per second, or miles squared per hour, right? Whatever the unit of measurement is divided by the unit of time. Cool. Let's do more, right? So I would say the ones where it's just like a shape getting bigger or smaller are usually, I feel like, the more straightforward ones, right? Like, for example, I'm gonna let you all try your hand at this one. If I said we'll switch it up and go that way. The volume of a sphere is increasing at a rate of 100 cubic feet per minute. How fast is the radius of the sphere increasing when the radius is, sure, let's say 10, let's say 5 feet. So I want you all to do all the setup. So do your step 1, the things that are changing. Step 2, the equation relating the volume and the radius. Step 3, differentiate both sides. Step 4, plug in and solve. And I imagine you were expected to know the volume equation of a sphere, but in case you've forgotten it, we'll remind you that the volume of a sphere is given by 4/3 pi r cubed. And I'll give you like 3 to 4 minutes. We'll see how people are doing. I'll try to give you time. It's hard for me to be quiet.